Gunther. It's really a great pleasure and an honor to be here to discuss what's really a remarkable synergy between NASA's space science program and the Keck telescopes. And it's really not an overestimate to claim that the past 2 decades, the combination of ground and space observations have revolutionized almost every aspect of astrophysics and planetary science. And a lot of the intersection of those two takes place right here at Keck. And fortunately, the excellent speakers who you heard from yesterday and you'll hear from in the rest of the day will address most of these compelling topics from really the scientific background. And so I'm not going to try and do that. What my goal is in this short talk is to describe broadly what Keck has meant to NASA's program and why NASA continues to be a 1/6 partner in the observatory and continues to value that even in fairly difficult budget period. In our calls for Keck proposals to the NASA community, we require specifically that the proposers demonstrate really direct links to NASA's strategic science goals. They either have to address the overarching themes, or they have to propose critical support for an ongoing mission, or lay the groundwork for future missions. So what are these goals? Well, this is stated in the most recent strategic plan from NASA: expand scientific understanding of the Earth and the universe in which we live. Discover how the universe works, explore how it began and evolved, and search for Earth-like planets. Ascertain the content, origin, evolution of the solar system and the potential for life elsewhere. Now, fortunately, astronomers are a fairly crafty bunch, and any smart astronomer can drive a truck through one of these different topics and come up with something that says how the universe works and so on. But we do take it very seriously, and it's an important part of how we judge proposals to NASA, how they fit into these goals or support the specific missions that NASA has ongoing or planned. So in my talk, I want to discuss a little bit the history of the NASA Keck enterprise and how it highlights that it's not just science that drives NASA's selection of projects and what it supports, but it's really also the link to the project. So I'll touch on exoplanets and solar system exploration, and then I'll highlight 2 examples where Keck has really enhanced the return from the space missions, and that's also something NASA values very highly. And then finally, I'll look ahead a bit to see where NASA and Keck are going in the future as NASA prepares its next big thing, the James Webb Space Telescope, and how, as some of you may not know, Keck was instrumental in demonstrating some of the key technologies for JWST. So if we go back to the dim mists of time, no clicky. Okay, we'll do it with the mouse. Yeah, no, I've got the clicker, but it's just not doing anything to my computer, not surprisingly.
I think I can put mine on.
Yeah. Oh, I see, yeah, it needed to have that. Here, let me. Okay, that. Okay, there we go. You got it. Thank you. Okay, so in the beginning, as far as NASA is concerned, there was something called the TOPS report. Ed alluded to this, and it was towards other planetary systems, and it was a report to the Solar System Exploration Division back in 1992. And the first phase of the TOPS program is centered around a ground-based observing program. This is how we are going to get to the discovery of Earth-like planets beyond our solar system. Discover and study planets with masses as low as Uranus and Neptune, around 100 or more neighboring stars. The defining element of TOPS 0 is the Keck 2 telescope. What a fabulous moment when NASA decided to come in and help support the building of Keck 2. So it called out 4 specific things: telescope construction, check; enhance image sharpness, that's adaptive optics, check; focal plane instrumentation for studying planetary phenomena and material around other stars, check; and build an interferometer using the two Keck telescopes. So all this led to what I call the beginning of a beautiful friendship. And you can figure out which one is Ed Stone and which one is Wes Huntress, all by yourself. But if you look at it in the NASA terms, between Keck and NASA, the beginning of the beautiful friendship really coincided with the two Kecks coming online and the Hubble Space Telescope with its servicing mission, which really began the Hubble mission. And that led to a really remarkable confluence of scientific interest and discovery. So this is simply a plot of refereed citations where I simply looked in Keck plus Hubble, Spitzer, Chandra, and so on. And so enormous publication rate where Keck and HST data went in to making some discovery. And these are all, in many cases, very highly cited articles, some with more than 1,500 citations and at least one Nobel Prize and a couple of other prizes along the way. And then Spitzer in the infrared, Chandra in the UV, HST, Spitzer, and Chandra, very productive. IRAS, here's all of Tom Sofer's work. Kepler catching up very quickly. And then a whole suite of other missions, including planetary missions and so on. So it's really been this confluence of ground and space that has been so remarkably powerful. And Keck plays very well with NASA science. So this is the exoplanet part, and you can see here, as the years tick by, we start getting more and more planets. We're at 1999, 2000, and these are all the radial velocity planets. Oops, here's a transit coming in, more RV, a couple of imaging systems, lots of transits, and then we get to 2012. Now, next. Let's do it. Okay, so here's 2012. Here's all the different kinds of ways of finding planets. They're in this mass and semi-major axis plane. And we have imaging, RVs, transits. And the remarkable thing is that Keck has played a role in all of these. We saw some of these great results yesterday. Jeff and his colleagues pioneering high-res, NASA contributing to an upgrade of high-res because it was in the program's interest. All the Kepler work doing confirmation with high-res or adaptive optics of many of the Kepler objects, and of course, as Bruce McIntosh described, the Keck imaging with adaptive optics. So here's a planetary system. We saw this yesterday, 8799, with the lovely spectrum of this object from Osiris. But the NASA goal, remember, is to find Earth-like planets, and this is the scale of 20 AU. Down in here is 1 AU. We need to get all the way in closer to an object in that close to its parent star, and probably 100,000 times fainter than the objects shown in here. So this remains a major challenge, certainly for Keck, probably beyond Keck, maybe some of the other large ground-based telescopes, but eventually something that will do from space. There's a major problem, of course, that we know that young stars or even mature stars have dust associated with them on all physical scales. Here's the dust ring around Fomalhaut. Again, we want to be looking for planets in very, very close. Maybe not around an A star, but about lower mass stars. And this exozodiacal light challenges planet detection. And NASA recognized this early on. Stars are 1 billion times brighter than a planet, which is symbolized, hidden in this glare, like this firefly hidden by the glare of the star, and you have to get rid of that. And then there's this exozodiacal fog that you have to look through. So one of the reasons that the interferometer was built and why NASA bought into Keck was to probe this problem, and one of the major technological challenges that Keck pursued was to link the two Kecks together to make an equivalent 85-meter baseline telescope to pierce the exozodiacal fog. And if you ever get a tour of the summit, go down to the basement, there's just a whole lot of hardware down there. And a whole lot of people put in a lot of effort built around this one NASA goal, which was to understand the exozodiacal emission around the stars. Were these stars clean enough so eventually we could find planets around them? You take a star here with a dust cloud, the star is very bright. You put a null right at the position of the star, get rid of the starlight, and you can start to see the emission. So on Fomalhaut, which I showed earlier, Keck interferometer indeed found dust at a wavelength of 10 microns, very hot dust, sitting at around 2 AU from the star itself. We looked at a lot of other stars that are much more solar-like, and were able to set limits of a few tens to a few hundreds of zodies, and Keck has set the best limits to date on the habitable zone dust, improving on Spitzer by about a factor of 5 to 10. And that pretty much is where the Keck interferometer hit its sensitivity limits, and at that point NASA decided it was time to do other things. Remember, good science is not always NASA's goal. It's find a project, do it, move on. And it did. Let me shift now to solar system, where again this combination of science and mission support has been very important. Mercury Messenger is sitting at Mercury, mapping out that planet, but so here's a full image of Mercury, but it's been monitored from Keck using high-res for over a decade, carefully scheduled by Barbara Schaefer and her team of herself. And every time high-res is on the telescope, Barbara manages to sneak an hour or two in there, and we were able to find very early information that helped Messenger figure out what sorts of measurements it wanted to make when it got there. And of course, Messenger did even more, finding even ice in the deep craters at the North Pole. Okay, we heard a little bit about deep impact from Mike Muma yesterday. Here's another deep impact that we just dodged. Here's another one that we would like to dodge, and that gets to the whole question of near-Earth objects. And that, of course, is something that NASA's been charged to worry about by Congress, and it does little bits of it along every once in a while, and Keck has contributed there with Bill Merlin actually using the adaptive optics system to resolve some of these NEOs. Here's one that's about 250 meters across. It missed. It's okay. You would have heard about it. Here's a binary NEO. We start to learn that we could send John McClane to blow this one up, and he would still get hit by this one. You never know, but this is sort of an ongoing kind of science where Keck again has played an important role to understand some of these objects. Mike Muma talked a bit about the study of methane on Mars. Here's a NIRSPEC slit that was eventually stepped across the whole surface of Mars. Here's a derivation of methane abundance in quite specific areas highlighted here. And it showed up in 2003 and has been hard to find since then. Is it instrumental? Is it time variable on Mars? I think that's still an ongoing question. But these data were very instrumental in defining some of the Mars exploration in the years after 2003. And finally, Mars Curiosity got there and solved the problem. That is where the methane went, or that's where it came from, and there won't be any more. And you move out from Mars, and Keck, of course, was instrumental with the work of Mike Brown and others in killing Pluto as a planet. Now, NASA spent $650 million to send a major spacecraft out to a planet, not to a dwarf planet. And there was a recent AAS where Alan Stern, I guess Neil Tyson and I debated the wisdom of this demotion or reclassification, but New Horizons was already on its way, so there's nothing Congress or NASA could do to pull it back now that it was no longer a planet. And in fact, one of the issues that's come up is here's the trajectory of New Horizons going through the Pluto system. I'm not sure if the angle is right, but it does get that close. That's about 10,000 kilometers. And as more moons have been discovered around Pluto, the team has started to worry that as they're cruising by at 14 kilometers per second, if they hit even a small piece of dust in a ring or a small moon, the mission could be endangered. So Taft and Barbara and NASA were working together to make sure NASA could use some of its Keck time, which it purchased explicitly, to go investigate the dangers in here using adaptive optics to look in very close to the Pluto system to see if there are any other moons. They also used Hubble, and so that's been ongoing, and I think the flexibility that Taft showed in making time available within a scheduled semester was very important. New Horizons is also using the Keck access to Subaru to look for new Kuiper Belt objects that could become a target for Pluto after its passage by Pluto, and it would be subsequently characterized by Keck, and we're very grateful to the Subaru Observatory for working with us to make that possible. As I mentioned, a lot of what NASA does with Keck is try and extract mission support, one sort or the other, but there is really a lot of interest, and NASA appreciates how the science return from the science missions is enhanced with Keck science. I'll mention just two things. One that I'm involved with is this is the WISE survey that Mike Liu talked about 100 times more sensitive than IRAS and really able to get down to probe ultra-low mass stars or free-floating planets, the very cool brown dwarfs. I won't go in detail, but if you have a brown dwarf, it has a strong emission here between absorptions of methane and water. So a very cool object with this sort of a spectral energy distribution shows up as green, and WISE has been able to find quite a few of these, many of which have been followed up by Keck. So Mike Cushing had a lot of NIRSPEC work on this, where we probed the spectra of these objects, trying to determine their physical properties. And these things are basically room temperature planets. They're 5 Jupiter masses and 300 Kelvin. They're free floating. And one of the big questions, of course, is how many are there? This was asked as a question yesterday. And a number of us, myself, Chris Gelino, David Kirkpatrick, are using Keck to get parallaxes of these objects at 23rd magnitude to try and find out how far away they are. One of these objects is about 12 parsecs away, and from that we can get a sense of the frequency of these objects. Early on, people thought that just as M stars were more abundant than G stars and so on, low mass stars would continue to climb in abundance with an increasing number as you went to lower temperature and lower mass. In fact, they're flattening out and maybe even decreasing, and that leads to the suggestion that we're seeing the low mass end of the star formation process. You just can't make clumps of gas of a Jupiter mass or less stay together long enough to actually form a ball of gas that becomes a free-floating object. You have to shift to the planet formation core accretion process that we see around planets. So I want to come to the last bit of science, and this is where it comes back to the beginning of the beautiful friendship. One of the most important images put out by Hubble was the first Hubble Deep Field, and as it came out in 1996, Keck was right there and provided immediate spectroscopic characterization of objects in the Hubble Deep Field. Judy Cohen and colleagues came out in that year with about 140 redshifts at sort of Z of a half to 1. Later had another paper where she came out with another 670 redshifts. Chuck Steidel and colleagues found some of the most red objects. And if you look in the literature, there's over 170 articles that just combine Keck and various Hubble deep fields. And this has been a critical part of the understanding what was in the Hubble Deep Field. So in that same year, Maddow published what has been called the Maddow diagram. Chuck called it this peak in star formation somewhere in here, the troubled adolescent years of galaxies. But this was first hinted at and much later elaborated in great detail. But the combination of the photometric redshifts validated by Keck and the Keck data themselves really led in the first couple of years of the first lights of Keck and Hubble to a transformation of extragalactic astronomy, really forever. We really started to explore the distant cosmological universe. And you'll hear much more about this in the coming talks. I'll just go through these very briefly. Keck has really been critical. We've had the great observatories, deep survey that involves Spitzer and Chandra and Hubble, and in that we really should be including Keck as one of the great observatories that has contributed so much by providing the spectroscopy. So this is just one example. This is I guess an ACS image of a cluster looking for gravitational lensing. There's two little blips in here that are images of a lensed galaxy at a Z of 6. The redshift, of course, comes from Keck. And DMOS, the data that went into finding these things, comes from Hubble and Spitzer IRAC. So this is a galaxy at very high redshift. It's got an inferred age of something like 100 million to a giga-year, and that implies it formed somewhere around a Z of 10 to 18. So we're seeing those early galaxies, but of course the question is, we don't want to see them when they're 100 million or a giga-year old. We want to actually find the first like objects themselves. I won't talk about this too much. There's more talks about it, but Keck has worked closely to follow up on GRBs. Keck and HST supernovae observations revealed the existence of dark energy and a Nobel Prize, and rapid response from notification that a supernova or GRB has gone off to an observation at Keck has really been critical to have a target of opportunity part of Keck scheduling. So what's NASA's next big step? The question posed by the Decadal and by Alan Dressler's committee, where are the first light objects? And of course NASA's response to that is the James Webb Space Telescope. And NASA's very proud of showing here's little Hubble, here's big JWST, of course here's big Keck. And you'll notice a lot of similarities, as was pointed out earlier, segmented telescope, and a lot of the technology, it turns out, that went into JWST went into Keck. Now you saw these wonderful movies of building Keck on the summit, hundreds of people working for many years to make all this together. NASA doesn't need people. We just put it together in a couple of minutes. Plus 10 years and a lot of money. An awful lot of money. But what you don't know necessarily is that as this deploys, you still have to get these panels into very close alignment so you actually can produce a diffraction-limited telescope. And there were experiments done in 2003, 2005 using a camera from JPL to validate the overall technology of JWST using a combination of grisms and prisms to disperse the light from each edge boundary here between all the different segments. That produces a diffraction pattern that you can analyze. It leads to then measurements of the intersegment heights, and you use that to show that you can actually align JWST after it's first deployed to bring it into alignment and then start the high fidelity alignment with other steps. But the basic technology was demonstrated at Keck. Offsets were put in using the control system between plus and minus about 25 microns, produces this fringe pattern in the camera that was built, the dispersed Hartmann camera. These were analyzed, these fringes. It was figured out what to do to drive all the segments to the right place, and you can see that these commanded offsets really went down to a very low level, down to about 0.2 of a micron. And that's the technology that will be used with JWST, so when it goes up there, Keck will be responsible, one way or the other. But it was an important part to get the Mare design up to TRL-6. So Keck and mission support, I'll just really end with looking at this. This is just a number of the spacecraft that I've described that Keck has been supporting. I didn't have time to talk about all of them. Most of them made it to flight, a couple of them didn't. But you can choose your favorite one: Chandra, Spitzer, Hubble, Kepler, IRAS, WISE, planetary missions, L-Cross bouncing into the moon, JWST, and so on. So it's really been a remarkable 2 decades, and I think what's most exciting is that a lot of the science comes both from NASA observers and the broad community. We've had over nearly 600 programs with nearly 200 unique PIs in the NASA program. NASA COA archives that it does both with IPAC, NEXI, and WMKO makes all the data from all the partners available to the entire community. And this is a very valuable aspect of NASA's space science program. What's the future of the beautiful friendship? NASA has just renewed, to Taft's great relief, a new 5-year agreement to operate with Keck from 2013 to 2018. Key projects include the Kepler, continuing the Kepler key science to confirm and characterize planet candidates. There'll be a remarkably bright comet coming up in the fall, and new instruments and instrument upgrades are all under consideration that you'll hear about, have heard about, and will hear about from Taft, that complement NASA goals and missions, including in the future JWST. Thank you.